Howdy, students. So we are going to solve this problem. We're going to use something called an IFE table. That stands for initial final effect. The first thing you need to do with problems like these are in Celsius. Celsius does not work for this type of problem. So we are going to convert those into Kelvin. So it is always 78 degrees for the first temperature, plus 273.15 equals your temperature in Kelvin. We type that into our handy-dandy calculator, and we get 78 plus 273.15, and we get 351.15 Kelvin. Our second temperature in the problem, because it says the temperature is decreased to 25 degrees. So we need to figure that one out too, because it's in Celsius as well. Gives us 25 plus 273.15 is 298.15 Kelvin. Got to be in Kelvin because we can't have negatives. You can't make predictions with this if you have negatives. So the second thing we would do if we had different pressures with different units is to convert to the same unit, but we don't have those, so we don't need to worry about that step. However, we're going to fill in our table now. So initial is always going to be our 1s. Final is always going to be our 2s. So we're going to fill in what we know. A sample of gas occupies 300 milliliters. Well, that's what we start. Milliliters are units for volume, so we're going to do 300 milliliters right here. At 78 degrees, we already figured out that in Kelvin. That's going to be right here, 351.15 Kelvin. Then it's going to decrease to 25. So that's 298.15 Kelvin. And then, so we've got that figured out, we've got that figured out, we've got that figured out, and then it says pressure and number of particles is going to be constant. Well, because we can essentially divide both sides by that, and you're not going to change, I just treat these as 1s because they are not going to have an effect on this prediction. It says, what is the volume? So that means we are looking for this volume because it was changed. It will change. So our pressure is 1 to 1, 0. Our number of particles, 1 to 1, not going to change. Okay? The temperature here decreased. So I note that it decreased here. The volume here, we should predict. I want you guys predicting before you figure anything out. If the temperature decreases, the volume should decrease as well. If you put a marshmallow in a microwave, it gets hotter, and then it gets bigger. It expands. If, like we showed in class, if we heat up a gas inside an Erlenmeyer flask with a balloon on top, then it is going to get bigger. But reciprocally, just like we showed when putting balloons in liquid nitrogen, as the temperature decreases, then the volume should decrease as well. But we want to make a quantitative prediction. So we're going to use our new handy-dandy tool, P1V1, N2, T2 equals P2, V2, N1, T1. The P and the V are going to be on the same side. The N and the T for the starting time are going to be on the same side as well. But the P and the V are going to be opposite the N's and the T's for the same time. Now later, the final time, again, we have the N's and the T's together and the P's and the V's together, but they're on opposite sides of the equal sign. That's because these things are inversely proportional, and in relation to these other things, they are, so the pressure is directly proportional to the number of particles, and the pressure is directly proportional to the temperature. That's why they're on opposite. But this is our equation. Now we're going to substitute things in that we know. Pressure 1 is our starting pressure. It's going to be 1. Volume 1 is our starting volume. It's going to be 300 milliliters. Number of particles 2. We're just going to put 1 in there. It's not going to change. Temperature 2 is this one, 298.15 Kelvin. Pressure 2, we're just going to call 1. Volume 2, we don't know, so we're going to solve for it. Number of particles 1, starting number of particles is just going to be 1. And the temperature at the beginning, the starting temperature, or T1, is going to be 351.15 Kelvin. Okay? So now we're just going to simplify. So we're going to multiply these things together. 1 times 300 times 1 times 298.15 gives us 89,445 milliliters times Kelvin. And this, we're just going to combine things. 1 times V2 times 1. That's just V2. And 351.15 Kelvin. Now, we're trying to solve for V2. So we're going to divide this over by dividing both sides by it. 351.15 Kelvin. 351.15 Kelvin. And our kelvins will cancel. 351.15. 351.15 cancels. Kelvins cancel. And we get V2 is these things. So 89,445 divided by 351.15, which gives us 254.7 milliliters, because those are the units that are left over. And that is what we would predict for an ideal gas would be the volume. Now we check our initial volume, 300 milliliters. We look at our predicted final volume. Hey, it did indeed go down. The IFE table does support what the math shows, and that sounds great.